Okay. Well, welcome again to another installment of Eclipse. Today we have Dr. Don Pakey, an emeritus professor of physics who retired last July. During his career, he had many varied interests, including astrophysics, neutron stars, asteroid light curves, etc., nonlinear physics, chaos theory, foundations of quantum mechanics, and not listed here, but mirages. He spent some time looking at mirages. He received his BS in physics and BA in mathematics from Eastern Illinois University, and master's and PhD from the University of Illinois Champaign. And with that, it was a pleasure working with him as long as I did, almost his entire career, not quite. I will leave it to him to tell you all about eclipses, the science.
Okay. Let's see, how do I turn this light off overhead so people can see the, is it right here?
Nope.
Nope.
Yep.
Okay. Okay. And we think we got that set for record and everything the way we want to think. Maybe. Okay. Well, welcome everyone. Yes, Steve had asked me for the title early on, and I said, I don't know, I'll think about it. He says, oh, for now, I'll just put science in there. And said, it never changed. But actually, what I decided to focus on was a really conceptual approach to eclipses. Back when I was teaching astronomy in the physics department, in one of these gen ed courses, what are they really going to take away? You throw in a lot of technical stuff for sure, but astronomy is really ancient. People have been looking at the skies forever, and to be able to really know what it is, how things are moving in the sky, I think is really important for everyone. You can get to the point of telling time from the moon and that sort of thing. But since we are focusing on eclipses, that's going to be my focus. Is really trying to get everybody to be able to sort of picture the motions of these heavenly bodies and, look at what actually happens. So, let's see, is this turn on? Okay. So on April 8th, there is an eclipse. An invisible dragon will devour the moon. True or false?
True.
Well, in fact, it's false. This is a solar eclipse, so the invisible dragon will be, in fact, devouring the sun. That's my only joke, so you gotta like that one, okay? That's my only joke for the whole talk. You can laugh whenever you want, but that's the only joke. Okay. Okay, so what is it really? Okay, this is obviously not to scale, but what are we seeing? Okay, I'm pretending like I'm back in class. What type of eclipse is being depicted here? It's a lunar eclipse, right? This is where the sun, earth, and moon are aligned, and the shadow of the sun is covering the moon. We've probably all seen them at some point or other. They're a lot more common than solar eclipses. So lunar eclipse, that's a lunar eclipse. I'll say a bit more about those because I need to fill 50 minutes, okay? Okay. Yeah, so eclipses occur when the sun, earth, and moon are all in a line. If Earth's in the middle like this, not to scale, obviously, the shadow falls on the moon, you get a lunar eclipse. And now this is one of the things I really want to focus on, is the relationship between the phases of the moon and the type of eclipses that you can have. So, but our thinking caps, we're not doing a lot of equations here. Can we all see that this is the full moon phase, right? A lunar eclipse can only happen at the full moon phase because when you're here on the Earth, you're looking at the lit up side of the moon. Okay, in this case, it's in the shadow, but nevertheless, the light from the sun is coming this way. And so we are looking at the lit up side of the moon. That would be a full moon. So, pretty basic. Don't start snoring yet, but this is really what I want to focus on. So a lot of people have never really thought about that. What's the phase of the moon right now? It was new a few days ago. I don't know if you've been able to see the crescent moon after the sunset yet or not. Tonight you'll be able to see it. Okay. So anyway.
And it's about a month until.
Indeed it is. April 8th which you might call March 39th, if you want to look at it that way. 30 days or 29.5 days before that would be the 9th of March. So more, give or take a day. That should have been when the new moon was, which would be when we could see a solar eclipse. But anyway, to finish up with the lunar eclipses, there's a partial and there's a total lunar eclipse. How many people have seen a total lunar eclipse? Yeah, a lot of people. And you know that it does, if you've seen it, it looks red. That's because of light coming through the Earth's atmosphere. The moon is in the total shadow of the Earth, but some light diffracts around. This is the same reason why sunsets look red. The same reason the sky is blue. Because if you look up at the sky, you see blue light. What does that mean? If the sun is, well, if the sun is over there and you look up in the sky and see blue, what does that mean? It means the light has gone from the sun, bounced off an atmospheric molecule into your eye. That means that the atmosphere interacts more strongly with blue light than with red. That means that when you look at a sunset, the light's going through a large distance, through a lot of atmosphere. The blue light has been absorbed or scattered out of the beam. What's left is the red. So it all makes sense. It's science. Science. Okay, nice. Any questions? Okay. Again, not to scale. So moon revolves around the Earth and goes through a full cycle in its synodic period of 29.5 days. And synodic just means how long it takes to get back to the same phase that it was at. And that's a bit different from what we would call the sidereal phase, which is how long it just takes the moon to go around the Earth, because during that month, the Earth will have moved somewhat along in its orbit, so the moon has to go a bit further. I didn't put a slide on that because I didn't think it was that important. But anyway, the synodic one is the one we're going to be talking about. How long does it take to go from one new moon to the next new moon, or from one full moon to the next full moon, or whatever? About 29.5 days. Month is a month, or a moonth, if you prefer. Okay. In one day, the moon moves how far? So again, we're getting into this thing. We're supposed to be actually picturing the motions of these heavenly bodies. The moon goes around the Earth in 30 days. That's 360 degrees. 360 degrees divided by about 30 days is about 12 degrees per day. So you go out at a certain time of night. You say that tonight, see east-west, that you'll see the crescent moon out there. That means if you go out at the same time tomorrow night, it would be 12 degrees higher than that and a bit fuller, etc. So we see the whole thing. New moon, when you're seeing the dark side of the moon, again, obviously not to scale. Waxing crescent. Waxing, as we all know, means getting bigger, right? First quarter, some people would call that a half moon, but we call it the first quarter because it's 1/4 of its way through its phase. But right, so when it reaches that phase, that will be when the moon is overhead at sunset. So the lit up part is pointing towards where the sun is, which is on the horizon setting. Giving time to people. I mean, I'm not sure how hard it is for people to visualize that, but it's really worth the effort, to really think about, by looking at the moon, it's pointing at the sun, and so you can tell where things are situated. Whoopsie. There will be a quiz on this later. Gibbous, I looked it up, is actually pronounced gibbous, not gibbous. It means kind of fat. So this is a waxing gibbous phase. It's a bit bigger than half full, so it's gibbous, and still waxing, getting bigger. Then the full means moon's phase. Then the waning, the opposite of waxing, is waning. Yeah, but still gibbous. Third quarter, waning crescent, and back to new moon. So, yeah. Okay. Okay, now, the Earth's diameter is about 3.7 times as big as the moon. So that's kind of sort of the scale there. sun totally not to scale. But so the lunar eclipses do occur a lot more often than the solar. And think about this, if we have a lunar eclipse, everybody on that side of the Earth can see it. You don't have to be in an eclipse path or anything. Okay. Whereas a solar eclipse, this is the way it works, right? And I'm going to emphasize the two different parts of the shadow. The full shadow is called the umbra. The partial shadow is called the penumbra. But again, be really, just don't let it go by. Think a bit about what that actually means. If you are in the umbra, you cannot see any of the sun. You look this way, you're looking above the sun. Look that way, you're looking below the sun. If you're on the penumbra, you look across the top of this Earth, you can see part of the sun. So, think about it a bit. The umbra, the penumbra, pen means almost. Yes, Josh. Indeed. Umbro, what's that?
It's just
I don't know that word. What is it?
And much effects.
What does it mean? There you go. Thank you for that. Anybody else know more? Is it Latin or Greek? Okay. So anyway, the umbra and the almost umbra. Okay. Yeah, solar eclipses occur. Oopsie, doing that. Occur only when the moon's shadow falls on the Earth. Only at the new moon phase, right? Again, to emphasize, you're looking at here we are on the Earth. We're looking at the dark part of the moon. Okay, great. Okay, blah 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 blah. You see total eclipse and penumbra. I just said all that, right? So just another picture of the whole thing. But this is kind of a little expanded view here. So it looks like at this point that the umbra comes down to a point or a very small area on the Earth, and that is the total eclipse path. We're going to see more about that. Okay. So yeah, this is sort of a time lapse of what goes on during a total solar eclipse. And when you see this, if you see this, or even if you see, partial or total, you should be imagining, right? You know that what is happening is the moon is moving. And in another couple slides, you'll really understand how it is that the moon is moving in that particular direction. So yeah, the moon, progressively covers up more and more of the sun. Then you get the total eclipse, at which point you can take off your eclipse glasses and look at it with the naked eye. Like Steve was just saying, it looks like it's brighter here, but it isn't really. I think Dave last week in his talk said that when you're looking at the corona, that it's about 1 million times. Was it 1 million? I have to look back at my notes. Less bright than the normal sun. So yes, it is completely safe to look at when it's in the total eclipse mode. Okay. Right, and this is a bit of a coincidence. The sun is about 400 times larger in diameter than the moon, but it's also 400 times further away. Moon's about 250,000 miles away, and the sun's like 100 million miles away, if you don't mind me using miles. I'm retired now, so I can do that instead of kilometers. Okay. So what that means is that they have the same apparent size in the sky, the moon and the sun, about 0.5 degree. Okay. So yeah. However, that depends on what phase of its orbit the moon is in. The moon in its orbit around the Earth is not completely circular, it's elliptical. And so if the moon's near the apogee, meaning far away from, G meaning, Mike, this is for you. Geology. Earth. Okay. Anyway, right. What is that? Yeah, if the moon is near the apogee, it's further out, and therefore its shadow is smaller. And in fact, at this point, the umbra does not reach the Earth's surface. What does that mean? Well, you get an annular, not annual, but annular, meaning ring eclipse. And if you can kind of imagine that too, if you're right here under the point of that, you can look a bit in any direction, and you'll see a little ring of the sun around there. So that would be an annular. And by the way, This is something I did not know before. I'm actually not an eclipse expert. Just want to tell you that. I kept running into hybrid, and so yes, hybrid would be a particular eclipse that has an annular part and a total part, and which also means if I make a mistake, it's okay to tell me that I've made a mistake. Okay, but I'm making this part up, but I think it's true that as the eclipse path is going across the Earth in this case, there will be parts of the Earth where it's closer, which is where the rays are pointing directly towards the center of the Earth, and that would be the total part. But when it moves off to the side, it's further to the Earth's surface because of the spherical nature of the surface of the Earth, and therefore it would be annular at that point. I'm trying to get somebody to nod their head on that one.
It changes between full and
Yeah.
and
Okay.
angular. So yeah, you get that. And you're on the verge of being
Yes.
you're just barely
Right.
at the verge,
Yeah.
at the break point there.
Yeah. In fact, we had I think Steve, it was soon after you and I both got to EIU that there was.
Annually.
And it was an annular from here, but I live up in Urbana and it was partial from there. I was at work that day, so for me it was annular, but just moving that small distance was enough to make it partial in Champaign-Urbana. So yeah, okay. Okay, so our upcoming eclipse got about 115 mile wide umbra. It doesn't start in Mazatlan, but that's the first place where it sort of hits land. Mazatlan, Mexico, at about 11:07 a.m. Now I made this all into okay. I made this all back into Central Daylight Time because what you can see here is so it hits Mexico at 11:07 a.m. It goes. We're going to see more about that. Texas, Arkansas, different things. Illinois ends up exiting over at Newfoundland at 5:17 p.m. But in Central Daylight Time, the total time transpired is only 1 hour and 40 minutes for it to get, from here to there. So, just kind of keep that in mind, right? It's good. It's good to think about what it is and how long it takes sort of in real time. But we're going to be going into that in quite a bit of detail, actually. Why do I say Mill Shoals? That's where I'm going to be. Okay. So, yeah. Why does it go from west to east? I don't know. Maybe it's obvious to everyone except for me. I had to think about it a bit. Now, the Earth's surface is rotating like this. So if the moon was just like sitting there, the shadow would appear to move from east to west from our perspective. Right? Moon just sitting there. Earth's surface moving towards the east. It would hit the east coast first. And then after a while, California, it would appear to go from east to west. Again, excuse me if this is all obvious to everyone but me. Okay, here's the science part. No, this is the math part. Okay, it's science. Why does the eclipse path go west to east? Yeah, it's really nice to know that with very few exceptions in the solar system, everything goes the same direction. So here's our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Yes. Very few exceptions. So Venus actually has a very slow but retrograde, the wrong direction rotation. Planet Uranus is kind of on its side. There are rings around, Jupiter, Saturn, and Uranus and Neptune. But okay. But in any case, with very few exceptions, everything kind of rotates around in the same direction. Because of the way it was formed, it all condensed down from a big rotating cloud of gas, have all the little whirlpools, and things moving around in the same direction. And so usually when something is going backwards, it might be because of a collision. Okay, but this is important because this is what allows us to visualize, to know what direction things go. Now all you got to do is wake up in the morning and figure out, where does the sun rise? Answer, over there, right? So that's east, which obviously means that the Earth's surface is rotating that way. That means that the moon is actually moving that way in the sky over the course of the month. That means the planets are moving that way. Now, it's all relative to, you have to take into account the motion of the Earth, But if you really want to dive into, visualizing the geometry of that, you got to start out with that basic idea that everything is moving in that direction. The moon going around the Earth is going that way, which is why, like I said, tonight we're going to see the crescent moon there. Tomorrow night it will be there, and then there, and there, and there, and there. Okay. Again, forgive me if everybody already knows this. Okay, so moving on. Yeah, just more of that. It sort of rotates about the North Pole, the celestial 40 degrees 40 degrees latitude, so it's 40 degrees above. Everything appears to rotate. The sun's over there, it makes a big path like that. Something in the southern sky would make a path like that. Circles or partial circles rotating around that direction right there. Oops. Okay. Okay, so here's the math part. The Earth's rotation speed, the speed of rotation of any point on the Earth's surface, how far does it go in one day? 2 pi r, the circumference of a circle being 2 pi times the radius. If you're, and then the time is 1 day. So at the equator, the radius of the Earth about 4,000 miles. Another fun number to remember. 4,000 miles. Okay, so you put 4,000 miles in there, and you get the speed. Divide 2 pi r, you get about 1,050 miles per hour. 40 degrees latitude, we're up, you're going around in a smaller circle if you're at a higher altitude. It's a sine of the angle. It comes out to be 673 miles per hour, slightly faster than a jet airplane, right? So, jump in an airplane in Illinois and go to Los Angeles. It might take 4 hours to fly, but you've lost 2 time zones. So you only have to turn. It only takes 2 hours in terms of local time. So yeah, let's see what else. Okay, so if the moon were stationary, the umbra would appear to move westward at that speed. Okay, does it do that? No. This is the actual path of our eclipse coming up. Goes west to east as it goes south to north. Okay, so let's do this one too. Yeah. The moon goes around the Earth. Oopsie. Again, V is 2 pi r over t. We're now radius is that 250,000 miles to the moon. Okay. And it takes how long? A month. Now, this is from the Earth's perspective. So, we're just doing an approximate thing anyway. But in any case, put that in. You get about 2,130 miles per hour. So this is the moon actually moving from west to, towards the east. So this is an effect that would, in fact, cause the path of the eclipse to move from west to east. Luckily, it's a bigger number than that other number we came up with. So the net effect is that here where we are, 40 degrees north latitude, it'd be about 2130 miles, 673, or 1460 miles per hour, very, very approximately. So yes, the actual speed of the moon going across the sky is bigger, but not like 100 times bigger, just a bit bigger, several times bigger. And so, yes, solar eclipses have to go from west to east. Yeah. Any questions about that? Okay. Right. Okay, this might be too much. Let's see. Since the eclipse in Illinois is at 2 p.m., so it's going to be there. The Earth's surface is curving away. Now, I don't have a really good diagram for this. Maybe you can see it here. But again, if you want to do, try some three-dimensional visualization is not necessarily easy to do, but you can. So the fact that it's going to be happening, a bit past noon means that I don't really have a good diagram for this. That when the Earth is at you're sort of way over here, the Earth's surface is curving away from you, so the surface speed is going to be greater. As the actual path moves 1,000 miles per hour this way, because of a projection effect, it will be going particularly, a lot faster. Yeah. Boom, 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 boom. So the actual speed of the eclipse of the umbra here in Illinois is going to be like 1,900 miles per hour instead of that 1,460 from that. So I'm not a person could, if they're really interested in it, go a lot further into the geometry, but yeah, it'll be slow. It'll be approximately the slowest when it's noon. Now there's also a north-south effect, but But it does turn out that, yeah, when it leaves the Earth's surface in Newfoundland, it'll be going like 5,000 miles an hour, the eclipse path. Okay. And that's, it'll be about 5 p.m. local time. Yes, Josh. Yeah, indeed, that's right. And these eclipse paths are pretty hard to visualize, but as far as we can get with that, the further we can get with that, the better off we are. It's fun to think about. Okay, so here is an animation of this. Let's see if this works. Boom, boom, boom. Okay, good. So the big circle is the path of the outer limits of the penumbra, so that'd be the partial. And this is the path of the total, the umbra. Now, when you look at that, it looks kind of curvy. However, if I had brought my meter stick with me, which again, Dave wondered, this is actually making a straight line, as it must. Because, what's actually happening is that the moon is moving in more or less a straight line. I mean, it's over this time scale of a couple hours, it's essentially a straight line. But you have the curvature effect of the Earth and the rotation of the Earth, which causes the path on the Earth's surface to have this kind of odd shape. So this is great. I mean, if you can actually see that it is. So what's happening? We're going to go into that a bit deeper too. But the moon is not just moving west to east; it's also moving upwards or northward at the same time. Okay. Y'all may remember 2017 when the eclipse path on that one went down from the northwest to the southeast. Both of them crossing through Carbondale, Illinois. Any questions about that? Okay. Do you see why the eclipse path must start around 6 a.m.? Because when the umbra hits the planet, what local time is it at this side of the Earth? 6 a.m. I mean, okay, it could be 7, could be 5, whatever, but it's dawn, right? The Earth's rotating this way. So this point on the Earth is where it is going from dark into light. That's what we call sunrise at 6 a.m. Okay. And it must leave the Earth at approximately 6 p.m. Again, time of year, could be a lot later or earlier, whatever. So, and why it can never last more than about 8,000 miles over 2,000 miles per hour. Where did I come up with that? Oh, well, if the radius of the Earth is 4,000 miles, the entire diameter is 8,000, and roughly 2,000 miles per hour makes 4 hours. Give or take. Astrophysical precision. When I was in grad school, we defined this as you got the right answer in astronomy or astrophysics if you're within a factor of 10. Okay? Seriously. Okay. This is the point at which the recording may no longer work. I wanted to show this. I see I'm talking fast. Is that clock actually right? Oh, it is, isn't it? Yeah, okay, good. Anyway, so what we have is a nice simulation flavor video from greatamericaneclipse.com. Simulates a view from a spacecraft or something, 125 miles up. So maybe I'll run it at 2 times speed just to make it go a bit faster. But take a look at it on your own. I'll show it now, but let's just do it. Okay. Do we have internet? Oh, that's interesting. I had internet before. If we don't, why is that not working? Let's see. Oh, maybe if we're lucky. Oh, good. Okay, but let's go ahead and make it go 2 times. Oh, it is going 2 times. Okay, just went. We hit Durango, Mexico. Yeah. Okay. But this is someone put in a huge amount of effort into this because they're taking into account even the mountains and craters at the limb of the moon, they claim, and the Earth's topography. So it changes slightly according to mountains and elevation on the Earth, because somebody had a lot of spare time, I guess. But it's got duration, and so you see the speed is at this point going faster, and the duration of totality, you can have a look at that. The width of the path slightly changes as you go along. Okay, so let's see. Maybe we should do a thing here. Oopsie. Let's see, where are we? Just to see where we are. Let's back up just a couple, just right over to here. How about?
Just enter.
Okay. Yeah, there's Champaign. So where's Charleston? Is that Charleston? Oh, right there, right there. Wait, where is it? Right
North of Effingham,
Yeah,
between Effingham and Champaign, just about halfway between.
Okay, where's Effingham? Oh, there's
Third of the
okay.
way to Champaign.
Yeah, okay. So anyway, so we see that, for instance, Paris and Effingham are right on the edge of the eclipse. I just a friend of mine who found me on the internet. I used to doing when I was back in grad school many decades ago. Turns out he lives in Effingham now, and they have a family farm there. And this is the story since I have time. Yeah, when you're on this side, there's no totality. When you get just over here, you have totality. So the length of totality changes very quickly with distance as you move from there to there. So he said, okay, we got a 40-acre lake on our farm, right? And so I did a quick calculation that he would have 19 seconds more of totality at the southeast corner of his lake than at the northwest corner. Now that's, again, astrophysical accuracy. So I'm going to say 19 seconds plus or minus 5 or 6, but nevertheless, So again, the lesson would be that if you're going to see the total eclipse, you want to be close to the center, so you get more time, Okay, anyway, quickly going on. Indianapolis. I think you can actually observe this from Niagara Falls. We'll be coming up on in a bit here. Let's see. Where's Niagara Falls? Right there. Isn't that right? I think it's right. Yeah, Niagara Falls. There we go. Now, because of this projection effect, we see that the speed of the moon's shadow is increasing, because, again, the surface of the Earth is kind of curving away like that. And then into Canada, Newfoundland. And it leaves not only the North American continent, but also the entire Earth's surface about here. So that was it. And the other fun thing I found out while making this talk was that Newfoundland has its own time zone, which is a half hour off from the others, one way or the other. So there you go. Okay. Let's see. Yeah, I have no idea if this thing is still recording, but here we go. Okay. Yeah. Okay. At this point, it gets a bit harder to visualize, maybe. But last week, Dave Linton threw down the gauntlet and said, next week, Don will tell you more about the Saros period. So I had to read up on it. So I learned a few things, but there is so much there. It's sort of an infinite. A person, could study eclipse cycles their entire life and probably not even get all those ancient words memorized. But anyway, here's the deal. So yeah, we saw earlier on the plane of the ecliptic. All the planets go in more or less the same plane as they rotate around, revolve around the sun. Most everything's in the same plane, more or less. The moon's orbit is tilted by, that says 5 degrees from the ecliptic, being the plane of the Earth's orbit. So when it is new moon, and that's the time when we could get a solar eclipse, the moon's shadow is usually not going to be exactly in that plane. It'll be above, by which we mean north, or below. And by the way, there is no up or down in space, right? But we're looking at it this way so that rotation. So the eastwards is, everything's going around this way. And so that's northward. Let's see. Okay, so, but it does, you see, so we have a bit of a, I'm not even sure this is useful. Maybe it's not. But in any case, as the moon goes around the Earth, there will be two spots in its orbit where it goes through the plane of the ecliptic. And only at those two spots would you be able to get an eclipse, because otherwise the moon would be, well, here, let's look at it. So here at this point, the moon is below the plane, and so if new moon phase, the shadow goes below the Earth, no eclipse, But then if the new moon does, what are we doing? Okay, so if the new moon occurs at a point where it goes to the plane of the ecliptic, which we call a node, then you would get an eclipse. Then over here it's not here because the moon is, because of the orbit of the tilt of the orbit. Moon's somewhat above the plane at that point, so the shadow of the moon goes above the Earth, no eclipse. Then there's the other node, the two, And so we have the two nodes, which are the points where the moon goes through the plane of the ecliptic. The line through those is called the line of nodes. Okay. So you got to have two things happening at the same time to get an eclipse. For a solar eclipse, you got to be at the new moon phase, and you got to be, the line of nodes has to be lined up. You have to have sun. Well, you can basically say that the line of nodes has to be pointing towards the sun. Now, if you're a little bit off, you can still hit the Earth, right? But it doesn't happen very often, as we know. So let's dive into that a bit. Okay, so the line of nodes itself slowly rotates. So over the course of the year, we have the line of nodes, and it more or less stays pointing in the same direction over the course of the year, but not quite. It slowly rotates so that it takes, I think I just did that the wrong direction. Point towards the sun again in one, what we call eclipse year, which is 340. No, I did do that right. That's right. Yes.
20 days.
Yes. Right.
Which were 20.
Yeah.
20 days. Yeah.
Right. If the line of nodes is actually pointing the same direction all the time, it would be again pointing towards the sun 1 year later. Okay, I mean actually half a year later, but we're talking, I guess to simplify things, we are talking about an eclipse in this particular case where the moon's going from the south to the north. So we call that the ascending node as opposed to the descending mode. So the one we'll have in April 8th is one that looks like, which one is it? Okay, it's this one, right? Yeah, because the moon's coming around like this. And when it hits the node, it'll be in the process of moving from below the ecliptic to above the ecliptic. So that's an ascending node. Okay. So if it's lined up right like this, if the line of nodes stayed pointing in the same direction as the Earth goes around the sun for a year, it would point at it again 1 year later. But in fact, it's not quite a year. It's 346.6 days, which means that as it goes around, it is actually rotated slightly like that. So it is pointing at the sun slightly before one full regular year. If that's too much detail, that's fine.
So I mean, so in 17 we had in August, and
Yeah, that was on the descending mode.
The fall one. Then we had the October one. Was 7 years later, be 7 times 20 days, be 140 days there. So it moves. So you're 18 years you're building up to it.
Okay. So, of course, we have a word for this. It's called the eclipse year. How long does it take after the line of nodes is lined up with the sun? You'll have another similar alignment, which means not the one on the other side of the sun, but the one where, again, the ascending mode will again be pointing at it. Right. That's what we call it, eclipse year, 346.6 days. Okay, so if you have an eclipse, you could see a very similar eclipse when a whole number of eclipse years has gone by, a whole number of eclipse years, so that the line of nodes is again pointing at the sun, and a whole number of lunar months. It's got to be the new moon again. So it's got to be a whole number of lunar months. Okay, what are the chances of that happening? Not very good. Okay. Any questions about that? Again, that's a very important point here. If you have an eclipse, you're probably pretty likely to have another eclipse. Well, you'd be completely you know that there would be another eclipse if it were exactly a whole number of lunar months, because again, it'll be exactly new moon phase, and exactly a whole number of eclipse years, because again, the line of nodes would be pointing at the sun. Okay. Right. Well, you just start multiplying them out, saying, oh, you know, what kind of numbers do you have to multiply these things before they come out to be more or less right? Okay. And this is it. It's called the Saros period. Again, I'm not a historian. However, I think that this was first used, the word Saros was first used by Edmund Halley of Halley's Comet fame. But the attribution was wrong. So again, I'm not a historian, but okay. The smallest period of time for which this is approximately true is the Saros period, in that 223 synodic months, 223 months, yeah, synodic months, times between lunar eclipse, between new moon phases, is about equal to 19 eclipse years. It's not exact, but it's pretty close. And you work that out, it's like 18 years, 11.3 days. Okay, so what does that mean? Well, the fact that it's not exact means that the moon will be a bit higher or lower at that new moon that happens 18 years, 11.3 months later. The moon will be a bit higher or lower at that next eclipse than it was at this one. And that pattern continues. So you can, in this series, 18 years, some odd days later, you're going to have another eclipse, another one 18 years after that, another one 18 years after that, et cetera. It can only go on so long because eventually you drop off the bottom of the Earth, and it starts only at a certain point because it's maybe if it's coming down from the north, there's a first one where it hits the Earth, and there's a last one where it hits the Earth. So they tell me, I looked this up. The Saros series, a series of eclipses separated by 18 years, 11.3 days, okay, a Saros series, can't last more than 1,550 years, and it can't contain more than 87 eclipses. I got these all, you can look them up on Wikipedia or NASA or someplace. All the different Saros series. Not all of them because they go on forever. Okay. Now, how do you number them? Saros Series 1 was arbitrarily, they say, chosen to be the one that started in 2872 BC and ended in 1592 BC. Okay. The one coming up is in Saros Series 139. I didn't go into it enough to know in what order they numbered the Saros series. Sorry. But our favorite Saros series, number 139, is a series of 71 eclipses that started in 1501 and will end in the year 2763. Now, okay, as an odd number, they've chosen it in such a way that all eclipses of odd number Saros series are at the ascending mode, meaning that the eclipse path will be from southwest to northeast, as opposed to northwest to southeast. Did I say that right? Okay, right. So yes, the umbra will move from the south to north as it moves from west to east. After each succeeding eclipse in that series occurs. Oh, and then after that, okay, now did Dave mention that last week, or did I just, anyway, I think he might have said it. And I didn't look this one up, so I figured it out by myself. So if I got the wrong answer, now's your opportunity to show me up, okay? I mean, I did look up to see that this is kind of what actually happens. But here it goes. Okay, so let's say that an eclipse just happens to happen right when the umbra's right smack dab in the center of the Earth. Yes, indeed. So the next one in that series, 18 years, later. Well, it's an eclipse, so it's happening at the point of the new moon. But it turns out that it will occur at a bit southmost point. What that means is that it happened at slightly less than how many was it 19 eclipse years later? Slightly less. So the moon had not yet ascended above the plane. Robert's nodding his head. So I think I'm encouraged by that. But we know the fact is, though, that is the case, that eclipses in an odd numbered Saros series, which are all in the ascending mode, the eclipses do, each one is occurring at a slightly lower. So that tells us that when you actually compare those two numbers, the whole number of Saros periods, the whole number of lunar months to the whole number of eclipse years, the whole number of eclipse years is slightly less. Because let's see, when the new moon happens, the moon is right there. It hasn't quite reached, yes, the whole number of eclipse years will happen slightly later when the moon goes through it does work out. Okay, you'll all be glad to know, and no one's shaking their head, so I'm going to say it's right. Okay, and if not, well, you can rescind my speaker's fee, take my cookie back. Okay. Anyway, yeah. The Saros was used to predict eclipses as far back as 700 BC. Okay, and I will say that I looked this, I Wikipedia this one as well. And, it's considered to be a especially bad omen in that particular place and time, meaning that the king would die. So what does a king do in this situation? Well, obviously, you get someone to predict the eclipse. And what you do is you abdicate the throne for a few days, get somebody else in there, and then they, literally kill the guy. And then the king comes back in after the eclipse is over. It's all good. Gods are satisfied, Yeah. Works for me, if I were the king, that is. So that's the history part, if it's true. Okay, here's a map of all the eclipses of this Saros series. Okay, this is a pretty busy little graph, and I am kind of running out of time. So, okay, the next one in the series occurs. Oh, what the? Oh, okay, will occur 18, 11. Now we get into dive into the 0.3 part. Okay, what happens in a third of a day? The Earth rotates a third of the way around, which means that next eclipse in 18 years, 11.3 days, should happen like a third of the way around to the west, because the Earth will have rotated to the east. That should be around Japan. There it is, 2042. Okay, so here is 2024 to the west is 2042. The next one after that would be 2060. There's that one, And so, so there's also this factor of 3 in there, that in approximately 3 Saros periods, to be back to the same part of the globe that you were at before. Not exact, but more or less. So here they are. I mean, we are kind of running out of time, but look, this in 2024. If you look very closely, you can see the eclipse path going up like that, or so they're all there. And then if you're a troublemaker, you would say, but wait, these are going actually south. And didn't I say they had to go north? Let's let someone from the audience explain that. You got this one? I don't. I mean, it's just the curvature of the Earth.
Does it matter what season?
I think you got it there. The Earth has a 23.5 degree tilt.
So you got
right. And we're talking about north as being the direction out of the plane of the ecliptic, but the Earth itself is tilted by 23.5 degrees. So hand waving, it all works out. Okay. Any questions about this before I move on? Oh, this is a good one. Yeah, I just figured this out because I had a vacation in Thailand recently, so I became familiar with the international date line. So this one, boom, boom, boom. Oh, the 2042 one. Okay, so look at its path. It's like this. At some point, it's the international date line. What happens as you move into the east? As time zones progress, you're going like, 10 p.m., 11 p.m. Well, it crosses the international date. Well, let's say 10 a.m., 11 a.m. noon, 1 p.m. Anyway, cross the international date line, moving to the east, you lose a day. So the beginning of the eclipse is on the 20th, and the end of the eclipse is on the 19th. Good fun. Any questions about that? Okay. Yeah, I just saw that. I went, what? Oh, okay. Oh, yeah. Here we go. So in 3 Saros periods, 54 years and 1 month, the eclipse will occur more or less the same spot. And so 54 years ago, I remember this. I was home on the farm outside of Springfield. It was a sunny day. I thought it was warmer than that, but it was March the 7th, partially eclipsed 70%. So that was this one right here. The dot represents the center of the eclipse path. So, I was up here, and yeah, I remember 54 years ago. So yeah, my own Saros series. Maybe some of you do as well.
I was a child attending, I went to grade school here at Buzzard Lab School when that was a school.
Do you remember this?
Yeah, I remember being out there with a box on my head.
There you go. Any other questions? Okay, we're running out of time. So this is ours. Anyway, what to say about it? Nothing. Going to get 99.86% obscuration and all that stuff. You can look it up on the internet. Okay. Oh, was it time? Let's see. Do we have the time on here? I'm not sure. Oh, universal time. That's 12:47, isn't it? No, it has to be 2. No, it's 2:47 p.m. Yeah. Subtract 5 hours from universal time.
So the partials, the start of the partial would be 12.
Yeah. Is what? Is
The start is 12,
He's right.
12:30.
When he gets.
yes.
You get 1%.
That's right. And this is the maximum eclipse at 2 p.m., which is more or less the same time as total eclipse if you're in Southern Illinois. Yeah. Okay, cool. That's where I'm going to be. And okay, fine. Okay, so I could be done at this point, but I think Dave covered all this. But yeah, you do have to be careful. If you do, obviously, if it's partial eclipse, you can never look at it with unprotected eyes. There was some question about what kind of welder's glasses you need. I happen to have this on my slide from 2017, shades 12, 13, or 14, solar filters, etc. There's the boxes on the heads that we were talking about. Is the teacher staring at the sun? No, because the direction to the sun is out the back of the boxes, right? Right. If the sun's coming in and being projected and they're looking that way, so the teacher was not like Donald Trump, you may remember, on the White House, right? Remember that one? Okay. So there we are. Are we done? Let's see. Is there something else I want to say? Yeah, path of totality. If you get there, once in a lifetime experience, because at that point, as soon as nothing but the corona is visible, take off your sunglasses or whatever, your eclipse glasses, and look at it with the naked eye. Stars, you can see a few stars, the brighter stars or planets that might be out. Right. Okay, and since there's that, you can do that. What if you have an event on campus, which I actually know nothing about, but anyway, I'm sure there's also live streams happening. Okay, I'm flying through this because, oh yeah, I'm almost done. This is not our Saros series, but it's all eclipses, from whatever year to whatever year. So what do we got coming up if you missed this one? Well, in 2028, you got one, it goes through, looks like, is that Brazil probably? In 2026, Greenland, Iceland, just off the coast of Iceland. So I don't know, you have to go out on a boat or something, and then down through Spain. And that's the one, that's Mallorca, it's right there, but it'll be close to sunset, so not ideal viewing. But anyway, you can look that up. Okay, and then that's the end. However, last week, Dave said he was really adamant that I should show the video of 2017. Can I have 3 minutes here? Okay, here we go. There it is. Okay, so I took a group of students to Chester, Illinois, along with Dave Linton back in the day. And I'm the dude with the red Hawaiian shirt on and the hat, and that's my wife Alicia, who photographed this whole thing. She's got a camera on a tripod, and at one point she picks it up and tries to look at the sun, but she can't really see anything. But the important thing is, Dave really was adamant that I got to show this video because he says, the main thing is he was really emphasizing you shouldn't spend all your time taking pictures of it. You have to experience the moment. And you can really hear the emotion in people's voices and the excitement, as this all happens. There's storm clouds on the horizon. We do not get rained on. EIU students, some. Got one of our old telescopes here. You can see I'm projecting. You can see there, if you look carefully, the path. You can see a little bit of a sliver of sun that's being projected by the telescope. It just went total, didn't it? I'm still like, what's going on? Okay, it takes me a moment. It didn't really look like that, it's just a camera effect. It's a star or planet. Lights went on in the parking lot. It's strange the light looks. About the same, about 1 or 2 p.m. I can't remember exactly. August, hot day. Really cooled off during the eclipse. Nina Geis and her daughters. Cicadas or locusts or whatever they are coming out and singing. Oh, maybe that's it.
Okay.
No kings were killed in the making of this video.
No what?
No kings were killed.
No. Anyway, that's it. So.
So I saw an ad or something that United or one of the airlines was willing to give you a flight to follow the path so that you could see the eclipse better. But if it's going at minimum 1,700 miles an hour, you're only getting an extra 30 seconds or something, right?
Yeah.
More than 30, but you're right. It's short because it outruns you.
Not to mention, the typical plane, you can't see out the top of it anyway.
I mean, from that height, maybe you can see the entire circle of the umbra.
Maybe, yeah.
I mean, I hear you, didn't somebody say they'd had that experience of like being on a mountain or something and seeing, you know, but no, it's not worth it, you know?
Edison, Thomas Edison.
Oh, okay.
In 1875 or whatever, 78, whatever it was, 18.
Yeah.
It was the Rockies that inspired him to go ahead and continue his work with the camera.
Okay. No, that would be another interesting aspect of observing the eclipse is to see it from a height, so you can actually see the motion of the, you know, of the shadow. You know, we could do that to a certain extent, you know, from flat Illinois. You can see, I mean, you can't see the edges of it or anything like that, but you can definitely see the shadow. So, yeah. Any other questions or comments? Thank you. Okay. Okay.
Well, thank you.
Well, great.